Long green.
So today we have another guest from Berkeley, Han-Bin Fung, who will tell us about coherent control of Tantivasadakarn, and we are very happy that you are here. So yeah.
Hello everyone, my name is Han-Bin. I'm a grad student in observables lab in Berkeley. Today I'm going to talk about my project on this coherent control of a spin qubit register in silicon photonics. So the system we study are called color centers, which are point defects in crystalline materials that created a localized defect state, which will introduce additional light absorption or emission feature. And therefore, if there's spins in the defects, you will get the spin-dependent optical transitions. So therefore, we say that color centers provide spin-photon interfaces in solid-state platforms. Moreover, these color centers are become ideal candidates for quantum computers because you have spin-photon interfaces, which could be used to generate spin-photon entanglement. Then the spins could be used to store quantum memory, and the photons can be used to generate spin-spin entanglement via entanglement swapping. More than that, if you also have nuclear spins in your defects or in the system, and you have electron spin in your defects, this electron spin and nuclear spin will happen from interacting. Therefore, you might be able to addressing multiple spin qubits with one color center. So the color center we study are called T-center, which are in silicon. So here is the believed structure of it. It consists of 2 carbon and 1 hydrogen in a silicon substitutional site. And this kind of defect, once it's in silicon, it will give you a light transition around the telecom orbit, which is 1326 nanometers. Because there is an unpaired electron on the carbon that is not bonded to hydrogen. If you put a permanent magnetic field around your T-center, Zeeman split will first split electron spin state. So you will have 4 electron spin dependent optical transition. Moreover, because T-center has a hydrogen inside, and hydrogen is a spin half system. So electron spin and hydrogen nuclear spin will interact, then further split your level structure. There are previous studies from other groups that they measured ensemble T-centers in a isotopically enriched box sample. And they find both electron spin coherence time and nuclear spin coherence time are fairly long. So for us, we create our T-center instead of being isotopically enriched silicon, we do it in nature silicon. So for nature silicon, there's around 92% of silicon-28, which is the majority. And it also has around 4.6% of silicon-29. And silicon-29 is also a spin half. So if you consider how many silicons are in the lattice around your T-center, the chance that you have a silicon-29 nearby your T-center is pretty high if you create your T-center in a nature silicon. So if that is happening, the silicon nuclear spin could also interact with the electron spin. So then we have to update our level structure proposal. Here I'm basically drawing the ground state manifold of a T-center coupled to both the hydrogen nuclear spin and the silicon nuclear spin, which give you 4 different nuclear spin states. So our goal is to do coherent control of a single T-center. To achieve the goal, we do a little bit of device integration. We first created our color centers via ion implantation and rapid thermal annealing. After that, T-center are created in the device layer of SOI wafers or chips. And then we do device integration for efficient photon collection and on-chip spin manipulation. So on the right-hand side is an overview of the chip we made. So let's first zoom in. For collecting photons, we just do a normal photonic waveguide, and later we deep etch the side so you can bring a lens fiber close enough to edge couple to your waveguide. Meanwhile, I also couple or pattern this meandered metal trace around my waveguide. So when you run AC current on it, it will generate a magnetic field that could be used to drive your electron spins. Moreover, when I measure it, I also put a permanent magnet that provides a magnetic field parallel to the chip direction. so that your AC driving from the meander trace could be used to drive the electron spins or the nuclear spins. Zoom out, this meander trace is connected to a on-chip called planar waveguide, where later we're using that to send in microwave driving signals. So after the device is done, we put the chips or we cool it down in a 4K cryo state. And for excitation paths, we usually do this on resonant excitation. So basically we have a tunable O-band laser that's sending the light from free space, and we focus the light with just an objective lens. And for photon collection, we first couple a lens fiber to the waveguide, and we collect the photons emitted in the phonon sideband and rotate that to SNSPD for photon counting. Moreover, the on-chip meander trace is connected to the coplanar waveguide, and we're bonded to the PCB and then connected to signal generators and all the other microwave components outside the cryo. So once the chip is done, the first thing we do is to measure the optical spectroscopy. So here, what we first do is try to measure the electron spin dependent optical transition. One thing for T-center is the cyclicity of it is pretty low. So if you imagine you are in the excited state and you're going into this decay to emit a photon, there's pretty high chance that the T-center will go through a spin non-conserving decay, which means that if you keep pumping one of the transition, after a several cycle, your electron spin will flip, and then your T-center will be effectively dark if you're only pumping with one laser. So to overcompensate that, we're using two lasers to do this pump and probe. So we're first using a laser on transition B to pump all the population on the electron spin up state. This is via optical pumping. So we basically initialize electron spin state. And then we're sweeping a second laser across this region. And when the second laser is on resonance with transition A and C, it will be able to make T-center bright again. So through this method, we're able to identify all 4 electron spin dependent transitions of the T-center. And we also verify that we can initialize the electron spin state with optical pumping. The next thing we do is we do a lot of optically detected magnetic resonance measurement, basically to find the electron spin transition resonance for all 4 nuclear spin states. So this is again you first use laser to initialize your electron spin state, and then you use several other microwave tools to again pump the population to the opposite state. And then when you sweep the second microwave transition, you'll be able to see different electron spin transitions pop up for different states. So here we were able to identify all 4 different electron spin resonance corresponding to different nuclear spin state. And later, we're trying to initialize our state in a pure nuclear spin state by using one laser. And for example, if we want to prepare on this state, we're basically using one laser on transition C and then sending in a microwave frequency that on resonance with 2, 3, and 4. And then you are able to prepare your state in a pure nuclear state. And then after that, we start to drive these nuclear spin transitions with RF tone. So here on the right-hand side, I'm showing we are driving the transition between one hydrogen to flip one hydrogen nuclear and flip one silicon nuclear. All of them are around megahertz-ish frequency. So after we find all the resonance for this level structure, we start to study the coherence. We start to demonstrate coherence control and coherence time of electron spin. So we first again initialize in a pure spin state and apply microwave driving. At the power we use, we can do a electron spin pi pulse of around 19 nanoseconds. And then we also do a little bit coherence measurement. So we start from, for our electron spin, we start from a Ramsey coherence of around 2.6 microseconds. And we run up to XY8, which make it around 1.75 milliseconds. And on top of that, we also try to study the nuclear spin coherence time. So similarly, we also first demonstrate the coherence control of our nuclear spin. First, to do a pi pulse on silicon nuclear spin is around 200 microseconds. For hydrogen, it's around 100 microseconds. And then we measure the Ramsey coherence time. For silicon, the Ramsey coherence time is around 14 milliseconds. And for hydrogen, it's around 4 milliseconds, which are pretty long in this kind of silicon solid state system. So just a little bit of it. So here we're studying a T-center that couples to one hydrogen nuclear spin and one silicon nuclear spin. There's definitely a chance that if you plant more silicon-29 into the system, there's a chance that your T-center are talking or coupling to more nuclear spins. So we do want to explore, can we control multiple nuclear spins with one T-center? At the same time, we're trying to working on do this nuclear spin entanglement to demonstrate about state generation with two nuclear spins. With that, I want to thank everybody in our subgroup and our funding agency, and thank you guys for listening.
Yes, you do.
That's very inspired. Yeah. You can It's my great pleasure today to introduce Tantivasadakarn to give our two-part seminar. Nat is one of the young leaders working at the intersection of many-body physics and quantum information. He got his PhD at Berkeley, at Harvard, working with Nathanan, and was then postdoctoral fellow at Caltech. And is now going to be starting his own research group at Stony Brook in the fall. Next year. Sorry. Not actually that. Okay. Good. Yes, and he's done lots of very beautiful works on topological phase of the matter, new types of error correcting codes, including K codes, and thinking about how to use measurements to define and create framework. Oh, and that is around through Friday, and the schedule was sent up in case you're listening to talking on this one.
Okay, thank you, Vedika, for the introduction, and it's a great pleasure to be here at Stanford. So I was an undergrad at Berkeley, so I visited here a couple of times, but I guess this is my first time officially visiting the physics department. So I'm very glad to be here. And I guess I don't need a microphone, or can people in the back here? Yes, okay. So today I'm going to be talking about sculpting quantum phases of matter with measurements. And the goal today is sort of to broadly highlight the deep connection between different things in physics, gauge theories, error correcting code, and sort of the surprise connection, how measurements sort of tie them together more deeply than ever before. And I assume this is a pretty broad audience. There's experimentalists, so I'll try to keep the discussion pretty broad, but feel free to interrupt if you have any questions. So let me just back out of it and just start with a very big picture. So I guess in undergrad, we learned that our first course in undergrad, we learned the quantum mechanics unitary. We have the Schrodinger equation, and then from that, laser pointer. Oh, it's very dim. We learned very early on that, well, starting from the Schrodinger equation, there's a lot of physics you can just learn by taking the simple equation, studying various phenomena in physics. And for example, if you study particle physics, that leads to the standard model. If you study how different Hamiltonians or Lagrangians describe different materials, that leads to the study of phases of matter, and the universality properties leads to this rich classification of matter. So this already started, this story is already self-contained when we just think about unitary stuff, where we just have some Hamiltonian or Lagrangian, and we know the dynamics of the system evolves with the evolution of Hamiltonian, which is just a unitary process. But then there's a second thing we learn in quantum mechanics, which is there's actually a non-unitary part, which is when we try to make an observation. And we know that every time we try to probe our system, right, Born's rule tells us how this sort of wave function collapse happens. And now we are sort of forced to do this. I mean, every time we try to probe our system, whether it's you study materials and you need to probe some properties of your material, you're an astronomer, you're just looking for you're detecting photons from the sky, or you get LHC smashing particles together. Every time a particle reaches the detector or sound, you have to perform a measurement. And this process is sort of mysterious, right? We're sort of forced to perform something we have rules for, Born's rule, but at a fundamental level, we still really don't understand why this wave function collapse works, or is this the correct interpretation of quantum mechanics? Now you might argue, well, really the important physics that happens, right? Maybe it's just when these particles, when I smash these particles together, suppose you're doing this dark matter experiment, it's just these guys smash together, everything here is scattering and it's unitary. It's only when this particle reaches the detector, I have to apply this sort of rule that's given to me, but I only need to use that here. So the important physics is whatever happens here, and that's the unitary part. The non-unitary part, maybe I can sort of just, treat it as a flat plot. And it explains a lot of it. I just use that, it explains the experiment, so I'm happy with that. Right. So measurement is sort of, seems like it's decoupled from the interesting physics that we have been usually probing. And people might argue, okay, maybe we don't even want to think too deeply about this because you can get into a rabbit hole of like which interpretation of quantum mechanics is correct, at which scale does this wave function collapse happen, right? This is sort of conventional, as a conventional physicist, we're sort of in some sense trained to think like this. But now if we look in the field of quantum information, actually there are a bunch of non-unitary processes that happen all the time. So for example, when people talk about quantum error correction, measurement is a key ingredient. In fact, this is the only way we know how to combat noise, right? If you want to protect your information, this is the only way to read out information, to read out whether error has sort of plagued your system and try to correct it to keep your information safe, right? Measurement is also essential to perform quantum algorithms because you need to use this measurement to turn quantum information back into classical information, right? And that's the sort of reason we can use these algorithms in the first place. There are also non-unitary processes secretly if we don't have access to an entire system, right? You can consider an open quantum system, for example, a spin coupled to a bath, right? And if you don't know the information about your bath, then effectively this is sort of like a non-unitary process. So the question I want to pose today is, are we missing out by not thinking about these non-unitary processes in the physics that we're discussing? So for example, people in high energy, people in condensed matter, we don't usually think of non-unitary processes. But this is a staple in quantum information for people who think about AMO. You do that all the time, these non-unitary processes. So the question I want to pose is, are there any insights that we can sort of try to export and try to learn new physics, for example, energy and condensed matter physics? And also maybe this new physics will shed light on For example, perhaps new advances in quantum information. So that's the question I wanted to pose today. So is there anything interesting we can learn? In the context of what I'm going to be talking about today, I wanted to talk about one particular aspect. That's just these measurements, right? And I want to talk in the context of quantum many-body states. That's what a condensed matter physicist would say. A high-energy physicist might say these are sort of gauge theories. So they're sort of highly entangled many-body states. And they're sort of really closely related to these highly entangled many-body states are closely related to something in quantum information, which is quantum error correction and quantum computation. So I'm going to be trying to make some connections between these fields today. And in particular, the theme of this talk today is what capabilities can we unlock by learning more about measurements. And the summary of what I'm going to be talking about today, the take-home message of the talk today is that I'm going to show how there's going to be a particular type of measurement which we can do something called gauging. And gauging allows us to prepare certain many-body states that were hard to prepare unitaries. But if you use measurement as a resource, you're able to prepare this more efficiently than any unitary can. Okay. So the scope of today's talk will be by using these measurements as a resource, we discover a new hierarchical structure of quantum many-body states that we didn't see before when we were only thinking about it in the unitary framework. And this is, of course, a theoretical abstraction, but I'm also going to be talking about how this leads to efficient protocols to actually prepare interesting many-body states that host some quasi-particles called non-Abelian anyons in an experiment. And I'm going to be talking about some experimental collaboration where we use these measurement protocols to actually prepare the experiment. Now, there's actually secretly a second part of the talk where you can actually import these insights in turn back to quantum error correction and quantum computation. But it turns out that my collaborator, Margarita Davidova, has given a talk on exactly this topic about 9 months ago. And here's the evidence, and that's her, and that's Vedika. So, I'll be skipping that part, but just to keep in mind that such connections are existing. I'm going to focus on the first half of the talk today. Okay, so I'm going to be talking about a particular class of quantum many-body states called, and I'm going to use the high-energy terminology of it. It's called gauge theories. And gauge theories is actually one of these topics that is ubiquitous throughout almost all of physics. So for example, in high-energy, people talk about the standard model. That's a type of gauge theory. In condensed matter, gauge theories are a very good way to describe as an effective low-energy theory for a lot of phases of matter we are familiar with, such as the quantum fractional quantum Hall effect, for example. And in quantum information, it turns out that secretly these gauge theories are exactly what people have been using for constructing good quantum error correction codes. And I'll talk a bit about one example here, the Tor code, that it is actually secretly a gauge theory. Now, before I move on to talking about the details, I just want to give a bit more motivation on why are we thinking about measurements? In particular, you might be asking me, okay, it's cool to be thinking about measurements, but why is it important to think about it now? So let me try to give you 2 reasons to convince you. So number one is that recently there has been a resurgence of thinking about non-unitary physics across different disciplines of physics. For example, open quantum systems, I already mentioned. Sort of many-body version of that is, for example, studying non-Hermitian phases of matter that interact with the environment, and how we can classify or even how to define phases of matter for open quantum systems. There are also people studying out of equilibrium phase transitions, where you can have unitaries competing with measurements and try to see whether you can get new critical phenomena, for example. And some of these are purely sort of non-unitary field theories that you get at the transition. There's also some recent interest in high-energy physics and condensed matter physics studying something called non-invertible symmetries. which are symmetries that commute with the Hamiltonian, but do not necessarily need to be unitary. So we've been taught that we've been taught in quantum mechanics that sort of symmetries sort of have to form a group structure, but it turns out we can relax it. And as long as we can find some operator commuting with our Hamiltonian, that can still teach us about how it constrains the dynamics of our quantum system. So there's a lot of interest in studying non-unitary aspects of physics. The second reason is that these measurements, you can actually perform them very recently, actually in quantum devices. So for example, one of the capabilities that people can just recently do is something called mid-circuit measurement. And that means that depending on the measurement outcome you get, say in your quantum circuit, you use that to control what you do of your next operation. You can condition what the next unitary you perform based on this measurement outcome. And this means that measurements now, rather than as a readout, for example, your quantum algorithm, right, you perform some unitary and measurement is just a readout here. It changes the role of the measurements to now perform an active role rather than passive role as a final readout in sort of your quantum algorithm, right? And moreover, people have actually studied before that using measurements as a resource, you can speed up many quantum algorithms. For example, the thing I'm showing here is quantum phase estimation that people use for factoring in Shor's algorithm. And people have shown that this thing, depending on how many inputs you have, the depth of the circuit is linear. But if you use measurements interspersed in the circuit, people actually show that you can lower the depth of your quantum circuit. And then what I'm going to be showing today is that a similar trick, by using measurement and feed forward in a state preparation, you can lower the depth of preparing a many-body state from potentially linear depth to actually a finite depth if you use measurement as a resource. Okay. So mid-circuit measurement is something that, people have been dreaming about theoretically, but recently many platforms across different, whether it's trapped ions, superconducting neutral atoms, a lot of these within the past 2 years now have such an ability to perform mid-circuit measurements. So it is an exciting avenue for us to explore both theoretically, and now that we know that we can perform this in an actual device, that makes it even more exciting. Okay. So hopefully I motivate you why thinking of measurement is an interesting question to think about, and in particular why we should think of them now. Okay. So let me get to the outline of the talk. I'm gonna first review something called a Z2 lattice gauge theory. It has many different names across different communities. I'll quickly review that. And I'm gonna review this and say this is a particular many-body state, which is hard to prepare unitarily. It requires a linear depth circuit. But if you use measurements, you can actually speed that up to be a constant depth circuit. While this is known, I'm gonna show how to generalize this picture and show that there are a bunch of other many-body states or phases of matter that we can also prepare efficiently using measurement. But measurement is still not powerful enough. There are still some states that are still not in our reach, and I'll discuss what is special about these states and what makes them still hard to prepare with measurement. And then finally, I'm going to talk about some experimental collaboration where we prepare the so-called non-Abelian gauge theory, which poses quasi-particles called non-Abelian anions in a quantum device. So let me just pause here in case anyone has any questions. Okay, if not, let's get right into it. So I'm going to first talk about the Z2 lattice gauge theory. And this has a long history. In fact, depending on which community you come from, it has different names. In high energy, people call it the Z2 lattice gauge theory. In condensed matter, you might have heard of the word Z2 spin liquid or Z2 topological order. And if you come from quantum information, people call this the Z2 torque. And it's been invented since the 70s and particularly developed by people here in Stanford. But the setup is very simple. So I'm going to have a square lattice, and on every edge of the square lattice, I'm going to put a qubit on each edge, so a two-level system. And I'm going to have these poly operators, poly z and poly x. So you can sort of think of it as a mod 2 version of electromagnetism. So I'm going to consider a state which is a simultaneous eigenstate of two types of operators. One is a so-called vertex term, where for each vertex I have 4 poly z's pointing out of this vertex. That's one operator. And the second is a poly x for every plaquette around this vertex. Now these two operators for every vertex and plaquette commutes, because if I consider this plaquette here, z and x anti-commute twice, so they will actually secretly commute. So I can consider the simultaneous +1 eigenstate of all of these vertex operators and plaquette operators. Now, why is this related to electromagnetism? Well, you can sort of think of poly z as a mod 2 version of electric field, and poly x as a mod 2 version of the vector potential. So usually when we learn in quantum mechanics, for example, for light, right, E and A have these canonical commutation relations. If you write it as such, you'll find that z and x will also anti-commute. And now this vertex term is basically a discrete sort of mod 2 version of the Gauss's law, right? It's saying that this term looks like the lattice version of the divergence of an electric field, right? So this is just saying that I'm considering a state with no charge in the middle. And likewise, this plaquette term looks like the integral of the vector potential around a closed loop. And that's just detecting the magnetic flux through that plaquette. So the state I'm preparing is basically the state for which there's no charge and no flux in the mod 2 electromagnetism, so to speak. Okay. So what does this wave function look like? So for example, let me write in the basis where z is diagonal, which I've already written here, and I can denote the state with all zeros, the empty state. Now, all the z vertex terms will be happy because this state is diagonal, but it's still not yet an eigenstate of x, the plaquette term x. So to do that, to make it happy, what I can do is I can act by x, right? Just try to symmetrize this operator. So for example, if I apply x, I create an electric field, right? I create an electric field, right? I swap the value of z from 0 to 1. So I create a closed loop of an electric field down over here. And now this term will be happy because this plaquette term will be happy because under the action of poly x, it swaps these two configurations. So it's now a +1 eigenstate. So now I can repeatedly act this operator, right, on every plaquette. And now this wave function, which is a now complicated entangled state, is now happy. It's a +1 eigenstate of all these states. So you can think of it as equal superposition of the closed loops of electric fields, right? So closed loops of electric fields means you don't have any charge, right? Because the electric field cannot end, but also you can check that there are no magnetic fluxes in this configuration, right? Okay, so that's the state I want to prepare. Now, people have studied this unitarily, and it turns out that this state is actually hard to prepare. So in the land of complexity of quantum states, right? We can let us quantify this by the amount of entanglement. On one end, there are unentangled product states, right? Each qubit is in its own thing. There's no entanglement. And on the other hand, if you pick a random state, that's going to be really highly entangled. So there are two classes of states that we're interested in. One is these easy to prepare states, right? Starting from a product state, I might only need to apply, for example, a unitary evolution by a constant time, or a quantum circuit that does not scale in the system size, so a O1 depth circuit. And now on the other hand, these random states typically require a linear depth circuit, meaning as I scale my system size up, the depth of the circuit or the time of evolution I require will scale larger and larger. But now topological phases, or these so-called gauge theories, the one I just talked about, just lie in this sweet spot here. They're not too complex to be like a random state, but they're still complex enough such that I cannot easily prepare them. So it turns out that these topological phases are exactly states that require a linear depth circuit but still have enough structure to be interesting rather than a random state way out there. Okay. So what I'm going to show today is that, so people have proven that it's hard to prepare a topological phase or this long range entangled state with a finite depth circuit. You cannot do that. I'm going to show how we can use measurements to reduce the preparation into a finite depth circuit if you use measurement as a resource for this example. Now, you might think this is unintuitive because shouldn't measurement sort of destroy entanglement, right? Your naive expectation is that suppose, for example, if I start with the cat state, right? I perform a measurement to check whether it's dead or alive, and it collapses the wave function into two outcomes, which are now unentangled. So the impression is that shouldn't reading out information from your system reduce entanglement, right? And the resolution turns to be that if you perform a random measurement that is correct, typically you'll reduce entanglement. But if you fine tune what exactly you measure, so if you have control over what you do when, then you can fine tune that and actually increase your entanglement. So let me show how to do that. So what people have realized is that, and this has been realized in the quantum information community for almost 20 years now, they realized that, okay, let's start with the product state where every spin is pointing in the plus direction. So it's an eigenstate of poly X. So the Blaquette terms we want to prepare way over there are happy, right? Because it's a product of poly X, but the product of poly Z's are not happy. So how do we do that? Well, we just need to measure this operator, right? We just, if we can, so for example, if I can project into the subspace where this product of Z is 1, then I would be done, right? Because I project it down into that subspace, that's non-unitary. But in general, we don't have projection as a resource, right? We only have measurement as a resource, and the measurement outcome is random. But nevertheless, so the measurement outcome you would get would have this plus minus sign. You would project to the plus ZZZ or minus ZZZ. Now, but that's not a problem because even though the measurement is random, you can always apply an appropriate product of poly X's to correct these -1 outcomes wherever you find them back into a +1. So even though measurement is random, with this sort of so-called feed forward, where you condition the unitary you apply depending on your measurement outcome, you can effectively apply projection. And that allows you to prepare this in finite depth. It is finite depth because all these operators, Z, right, are diagonal. So I can measure them in parallel. They can all be done in one shot. Right? So that gives me a way to prepare that state with measurement efficiently. Okay. Now, how do you do that in practice? So if you talk to an experimentalist, they would say, oh, you cannot measure this 4-body operator, right? What you would have to do is you would have to introduce something called an ancilla, which is you introduce another qubit here. You sort of couple this qubit to the 4 neighbors, right? Such that now when you measure this qubit, you effectively measure this 4-body operator. That's how you would do it in practice. Okay, so currently the ancilla here is sort of a means in order for us to measure this 4-body operator. Now I'm going to give a different interpretation using this idea of gauge theory or electromagnetism to show how we can actually rethink of this picture. So it turns out that previously people have generalized this to, if you want to project to some subspace, then you can always measure those operators that you want to project down to, right? And that applies to an arbitrary product poly operator. That's what PY people call stabilizing codes. But here, let me explain how we can go beyond this. And it comes under this idea of so-called gauging. So gauging, in short words, is just something where you project into the gauge invariant subspace. The gauge invariant subspace is a subspace where the Gauss law is satisfied for every vertex, meaning there's no charge. Now, how do we do that? So suppose I start with some configuration here. The measurement I was doing back there is basically the Gauss law I was mentioning, right? So the thing we were trying to measure to put physics into it is actually the Gauss law. And the measurement outcome, this plus minus, right, is actually measuring the charge. So what we're trying to do is we're trying to measure, is there a charge there, right? And if there is a charge, let us apply the X operator to pair it up. And the X operator, if you are familiar with gauge theory, corresponds to the Wilson loop. So you can actually use the Wilson loop, which with charges at the endpoint, to pair up these charges that you measure as measurement outcomes. Now, what is the difference? Why is it helpful to think of it this way? Now, previously, this the thing on the vertex here, I treated it as an ancilla. It's a means to which I can measure this operator, right? But now I've told you that the thing I'm measuring here is actually, I'm measuring a charge here. So I've inserted this ancilla in a product state so that I can use it to measure this operator, right? But in principle, this thing that I insert over here does not need to be in a product state. It could have been in some highly entangled state, for example, right? And this procedure, what I'm doing is I'm turning whatever you give me on the vertex, you can think of it like as a matter field. And this procedure is sort of like coupling it to a gauge field and turning it into a gauge theory. So the previous way of thinking of it is the special case where you start with an unentangled product state, and this procedure turns it into a gauge theory. But now you can actually input anything over here that you give me, and this procedure will turn it to its corresponding gauge theory. In particular, we might even do this process over and over again to try to create more and more entangled states. And that's what I'm going to show, how we can bootstrap this up to prepare more and more entangled states by repeating this process. Okay, so the take-home message is we should not think, if we can generalize this by not thinking of this as an ancilla, but thinking of it as a matter field. And we are trying to make a gauge theory out of this matter field by performing that. Okay. Let me pause again here in case there are any questions. Okay. So let's continue. So now you can ask, I showed you how to prepare the simplest gauge theory that's based on sort of this sort of called group Z2. Z2 is just the group where there are two elements, right? So it's 0 or 1, binary. But you can ask, there are a bunch of other groups which we might be interested in preparing, right? And the more complicated the group is, the more, roughly, the more entangled that state is. So we might be interested in asking, how do we prepare this for more general groups? And now you might say, can we just repeat the argument I gave earlier and prepare more of these interesting states? Now, the problem is that the naive generalization doesn't really work. So I mentioned that what I'm doing is I'm measuring whether there's a charge there or not, right? And depending on whether there's a charge, I clean it up with some operator. Now, the problem turns out to be that if I want to measure something, for example, a non-Abelian group, what you're going to be measuring is you're going to check whether there's a charge there or not. But now, for more complicated groups, for non-Abelian groups, it turns out that this charge operator is hard to move. So usually we think of charges as some representation of some group. So it might have an internal subspace. And depending on whether it has an internal subspace or not, we're going to call that non-Abelian. So for a non-Abelian particle, it turns out that when we want to move it, we have to keep track of the internal subspace as we move along, which means that we cannot just drag it infinitely far all at once. We need to gradually apply circuits to move it. And people have shown that if you have non-Abelian anyons, you cannot move them arbitrarily far in a finite time. You need a linear depth circuit. So that sort of defeats the purpose, right, of preparing this state. You can just do it unitary with a linear depth circuit, and that would be equally good to trying to measure these charges and trying to pair them up. So is there a way we can get around this problem to prepare non-Abelian states? So let me give you the simplest example, which is a non-Abelian, and it's the so-called group called S3. So S3 turns out to be the symmetry of the triangle. So you can think of the triangle having a threefold rotation symmetry, right? 0, 1, and 2. And you can also have a reflection. Reflection swaps 1 and 2 while keeping 0 invariant. And now together, these operations actually do not commute, because if I flip before I rotate, right, that would make it rotate the other way. So it's in that sense, it's a non-Abelian group. Now, instead of measuring the charge of this whole group all at once, we can break it down into some substeps. So what I'm going to do here is, so this group has sort of like a qubit part, right? A 3-level system, and then a qubit part. So I'm going to start from the qubit part first. I'm going to prepare this 3-level system, and I'm going to prepare the analog of the toric code that I just mentioned. Instead of mod 2, it would just be mod 3, and there's some generalizations of poly operators. So I would first prepare this Z3 toric code, and then now the thing is, if I then measure the charge on the qubit side, right? Then these two layers, the qubit and the qubit, they don't talk to each other yet. Then I'm just gonna get a group, a Z3 toric code times a Z2 toric code separately, right? They don't talk to each other yet. The part that makes it non-Abelian is because this Z2 acts non-trivially on the Z3. It swaps 1 and 2.
Please talk for 1 second. So you have
Yes.
2 layers. The
Yes.
green is a
If
V2 torical.
Yes.
And what's the red?
Oh, right. The green is made out of qubits right now.
Okay.
The red is made out of qubits, so 3-level system.
So they're all just in this product.
It's still in the product.
Okay.
And then first I'm gonna, in the bottom layer, prepare the Z3 toric code.
By measuring
By
Z3 charges.
Yes,
and
by
then
measuring the charges. 3, yes. And now if I skip this extra process and I went on and I measured the charges here, then they haven't talked to each other. So in particular, there's an extra step I need to do, which is I need to apply some unitary. This turns out to be some controlled operator, which makes sure that the action of the qubit part actually flips this current. So there's going to be some control operator here to control this guy, sort of conjugate. And you act that piecewise on every pair. And then after that, you're going to measure the charge on the top here, right? And then this is going to turn out to give you this S3 topology. So when I say gauge here, it's actually in practice you're doing 2 steps. You're doing the measurement, and then you'll get some charges, and then you pair them up. And now you split that into 2 steps. Now, you could ask, why can't I perform these 2 measurements all at once? That would be like one shot, right? In order to prepare this. The problem is, because these charges, after this step, they transform under the Z2 symmetry. So they, in particular, if I did pair them up and I then measure the charge, it turns out that because the Z3 charge transforms non-trivially under the Z2 symmetry. In particular, it looks like a doublet now, right? Because it exchanged E and E bar. Once I measure this, this is going to become a non-Abelian any, and then now I have a problem pairing it up. So the reason I have to do the 2 steps is because I need to pair this up first, and then I do the next round of measurement, and I cannot do that.
Can you give some intuition why you need to have this control be in this direction? Like why you have to have it be on the Z rather than the other direction?
Right. It's sort of because you want the acting on a Z2, say with a poly X, right? To have this effect. So if I conjugate this poly X in the qubit side, I'm gonna get this guy out on the qubit side, which acts correctly on the qubit.
But could I reverse this entire process basically and still get S3 out if I say do everything in reverse?
No, because Z3 actually does not act back on Z2. So the Z3 is self-contained, but the Z2 acts on it. And that's why you have to do it this way.
Could you say why it's difficult to pair the non-Abelian anyons up again? So you said that it's if I want to move one across my whole system, that takes linear that type.
Right. So the intuition is like it might have an internal state. So you can think of it for this purpose, say it's a doublet. Right? It's a doublet, so there are 2 internal states. And when you want to move that, you have to keep track of that internal state. So you cannot just move it here before you cannot parallelize it.
But I guess the thing I'm confused by is you don't need to move it across your full system, right? You only need to move it to some other anyon that's nearby. That's
The reason is, but because your measurement outcome is random, there might be a rare case where you have only 2 charges, right? And they're arbitrarily far processes. So
that happens with probability that goes to 0 as the system side goes. So why is it?
Okay. There's a bit more subtlety than that, but what happens is you could also have a bunch of stuff, right? And even if you pair them up, you might still get a non-trivial outcome, and this is because they're non-Abelian. So even the cleanup procedure, you might not be able to clean everything up because they might not fuse back to the back. You might fuse it to something else. Right? For example, doublet times doublet, right, is a singlet transfer. So you might get more than one outcome. You might not always end up back in the singlet. You might end up with more garbage.
Right.
Okay, so this is for the simplest example of a non-Abelian group. And now to go out on to the extreme, we asked, well, are there gauge theories we can't prepare efficiently? So this seems to be like a good strategy, right? You break your group down into a bunch of Abelian groups, and for each Abelian group, you're just going to be measuring an Abelian charge, which you can correct efficiently. Now, are there groups which can be prepared efficiently, even using measurements?
Sorry, one thing, but, I couldn't have gauged the Z2 and the Z3 kind of calculated and then done the coupling.
But yes, that's because you need to do measurement and do the speed forward to clean up these charges. If you
Okay.
didn't, so here they're easy to clean up.
Yeah.
But if you left them, they would become a doublet, and then they would be harder. They would combine.
Can I like measure on the top layer, measure on the bottom layer, clean everything out separately, and then do something?
No, because otherwise they would not talk to each other.
So you've got a clean Z3 core code
Yes,
on the bottom layer.
Yeah.
And then what is the coupling doing?
it's a sort of like this control operator. So if the qubit is 0, you don't do anything. If the qubit is 1, you apply this conjugation.
Right, but what's
So
it doing?
what is it doing physically? Oh, yeah, I mean, it's just making sure, right, that the transformation of Z2 acts correctly on Z3. So it permutes E and E squared correctly in this state.
And then you can clean out the Z2 changes.
Yes, yeah. Any other questions? Okay. So for this group, I could break it down into Abelian groups. And apparently mathematicians have studied what groups can do that. And the answer turns out to be the following. So I don't know about you, but tennis is easy, volleyball is easy, but apparently soccer is a very hard sport. And the person that first said this is not me, it's actually Galois. So Galois says that if you have, and this somehow is related to algebra. So when you learn in algebra, your algebra class, you said there's a solution for the quadratic equation, like and cubic, quartic, but there's no solution for the quintic equation. And that somehow has relation to the soccer ball. So it turns out that the solutions, the symmetries of the roots of the polynomial for 5 on the complex plane could have the symmetry of the soccer ball. And it turns out that the symmetry of the soccer ball, so-called A5, which permutes 5 things, roughly, is too complicated to be broken down into a sequence of Abelian. And that's sort of why you cannot construct a solution for the quintic equation, because you have to take roots, right, and third roots and fourth roots, but you cannot build it up all the way into your desired solution. So that's sort of the reason why there's no solution for the quintic polynomial. And apparently this same math seems to show up in our state preparation. So if you have a gauge theory with the symmetry of the soccer ball, our claim is that we think you cannot prepare it with finite depth circuits on level. So if your gauge theory has the symmetry of a tennis ball or a volleyball, that's fine. But we're saying soccer ball is, soccer ball is too hard. So it gives us, so in the pure unitary case, everything seems to be equally hard. They're all linear depth circuits if you want to prepare these states. But now using measurements, some of them become easy, particularly these two. But still there's some that are too hard to be prepared by measurement. That's what we seem to be finding. So we don't have a concrete proof of this. It's a very physicist argument, but yeah, it would be great if some mathematician could prove this rigorously. So as I said, there are a bunch of different symmetries you can consider for your gauge theory, right? And there are different groups corresponding to symmetries of different objects. They're all hard to prepare from the product state. And this boundary here is literally a phase boundary. You can think of it as these are different classes of phases of matter under unitary evolution. But now measurements sort of dissolve these phase boundaries, but not all of them. So a lot of these now become preparable with finite depth circuits and feed forward. But still, there are still some complicated things which we still cannot prepare with finite depth and measurement. But for now, even for the easier ones, what we can provide is we can provide some explicit protocols to prepare all these gauge theories, and the word people use in mathematics is called solvable. This group is called solvable if you can break it down into these abelian groups, as I mentioned. And so we can provide you an explicit protocol to prepare this in a finite number of rounds of measurements, right? Of course, there are these that are too hard, there are groups that are beyond, but there are also other topological phases of matter that are not really described by groups. For example, certain Chern-Simons theory. We also have an argument that those are hard to prepare as well. Okay, so this is a new lesson we learned by looking at measurements that we wouldn't have seen if we only look from the unitary perspective. Okay, so another interesting thing is for the ones you can prepare, you can ask how many rounds of measurements do I need to prepare that state? It turns out that for the toric code, the Z2 gauge theory, you only need 1 round, right? I mentioned that the S3 needs 2 rounds. You need to prepare the Z3 first and then go into the S3. So you need 2 rounds of measurements. You might ask, what about the symmetry of the square? And the surprising thing we found is that, well, the symmetry of the square looks more complicated than the symmetry of the triangle, right? But it turns out that we found a way to cheat even more, and we can prepare it using only 1 round of measurement, even though the group is larger than the symmetry of the triangle. So I'm not gonna sort of explain why, but this is, in some sense, the simplest non-Abelian gauge theory that we can prepare using only 1 round of measurement. And so that motivated us to look into some experimental proposals to prepare this state. Okay, so this one I already told you how to prepare. I'm going to talk about how to prepare this next. Yes.
Do you know that you need at least 2 rounds to prepare this S3 gauge theory, or is it just like you couldn't think of a way to do it in one?
Yeah, we have a good, it's a physicist proof. The same argument as we cannot prepare that, but it is a physicist proof. So we approach this from this gauging procedure, right? But in principle, you could have found something that is not related to gauging, but somehow did this. Yeah, so I haven't been creative enough to roll that out yet. So yeah, it's still an open. Yes.
So you got these equivalence classes here. Should I think that if I want to create something that's like A5 cross A5,
yeah,
that is not possible in the concept unitary starting from A5?
Correct. That would also be in a different.
I see. So like anytime I want to sort of like cross with a new sort of non-easy thing, that there's a new class of
yes. Yes. So now let me pivot to talking about the simplest non-Abelian gauge theory based on the symmetry of the square. So let me just give you a very quick intuition on what are these non-Abelian gauge theories. So there are quasi-particles called non-Abelian anyons. So let me explain what an abelian anyon is first. An abelian anyon is, you can think of some analog of the Aharonov-Bohm effect. You have a charge and you have a flux, and you move the flux around the charge, and that accrues a phase. So you can get a phase by moving a charge around a flux, and there are 2 particles. And in space-time, you can think of it as maybe I create a charge, particle-antiparticle pair, same thing for the flux. I move the charge around the flux, and then I fuse them back together. So the space-time diagram will look like this, and they're sort of linked. So this linking in space-time corresponds to this charge, this phase. Now, what are non-Abelian anyons? I mentioned that non-Abelian anyons have this internal space. So instead of getting just a phase, it's possible to get a unitary that acts non-trivially in that subspace. So what can happen is that after this braiding, when you fuse back the particles together, you might not fuse back to the vacuum. So that's the similar intuition of like you have 2 doublets, right? You can either get singlet or you can either get triplet. So you can have this non-Abelian, people call this a non-Abelian fusion outcome. The outcome might depend on which internal state these guys are in particular. So that's sort of interesting, right? We want to find some quasi-particles in a 2-dimensional system which has this property. So people have been theorizing and figuring out how to realize this in materials, in solid state materials, right? And abelian anyons have been around since people found the fractional quantum Hall effect. So it's been like almost 30 years now. But for non-abelian anyons, we have theoretical proposals, right? But so far, not really a clear-cut evidence. So what people have been trying to do is some transport experiments, right? But actually, and it matches with the fact that you have non-abelian anyons, but actually trying to move them and observing this statistics has been really hard. Now, fast forward 30 years, now we have these quantum processors, and people have now been able to prepare this interesting Z2 gauge theory in a quantum device. So in 2021, there were 2 experiments, one from the Lucan lab at Harvard, and this one is from the Google team. What they did was they prepared this so-called simple Z2 gauge theory. But actually what they did was they prepared it a unitary way, which means you prepare it with a linear depth circuit, or adiabatic evolution, whose time will grow with the system size. Right? So using these measurement protocols, we were able to prepare this same toric code state with finite depth, and this is some experimental collaboration with Continuum. What I'm going to talk about today is the more interesting one, the non-abelian one, which we collaborated with Continuum. The paper came out last year, and it's been accepted to Nature, and notice the publication date, very romantic from Nature. Okay, so, yes. Oh, okay, let's see. Wait, I started at 10 minutes. Oh, is there for questions? Okay,
Oh, yeah.
let me see. Yeah, I think I can do it. So for Continuum, what they have is the trapped ion processor where they have 32 ions. They load it into this some sort of racetrack architecture, and they can move them around and shine lasers on them to do 2-body gates. And in particular, they have very high single gate and 2-qubit gate fidelity. So we use that to our advantage. And let's see, 5 minutes. Let me quickly sketch you what the wave function looks like. So recall that the toric code is a closed loop superposition of all closed loops, right? Every configuration you can think of, including that one. Now, what state are we preparing? Now, let's consider we have 3 copies of the toric code. I have a blue version, a red version, I superimpose that, a green version, I put that on top of each other. So right now, it's just 3 copies of the toric code. And it's an equal superposition. And it turns out I only need a very simple modification. I only need to add a -1 to every configuration where the red, green, and blue sort of cross in this pattern. And that's and this is a local thing. So you can add this modification locally. And this turns out to have a very interesting consequence. It turns some of these abelian anyons into non-abelian anyons, turns out. And since this sign can be prepared locally, that gives us a very easy way to prepare it. We sort of prepare this minus sign first. We start with the product state, prepare this minus sign. So this is some diagonal thing that does that. And then we do this gauging procedure. So we couple these matter field to gauge field, measure, and then do the speed forward. So it can be simply explained in one line what our preparation is. That's the quantum circuit we apply. Okay, and the state you can describe similar to the toric code as some more complicated version of Gauss's law, no charge, no flux condition. The details don't matter, but the important thing is that now we can check how well we prepare the state, right? After we prepare the state, we went ahead and measured these operators to see how close we are to the ideal state. So this is the result. So in the ideal case, this would all be +1, right? But here we're seeing they're all like +90, +80. So they're all in the 90% range. And with that, we can bound the fidelity of the state we get per site to be 98.4%. So a pretty high number. Okay, since I'm running low on time, there are a bunch of things where you could use to determine how we prepare this non-abelian gauge theory. Let me just skip to the last one, which is the most interesting one. So I mentioned that in the toric code, abelian anyons, right? You have a flux and you move a charge around it. And in space-time, it causes linking. So this phase you get is only sensitive to this pairwise linking. But now consider this funny configuration where I have 3 loops that are sort of linked, But if you notice, if I remove the green loop, the red and blue are actually not linked to each other. But all the three of these are in fact linked. You cannot unlink them with all three present. And it's called Borromean rings because there are these, it comes from this coat of arms in this family in Italy where there were three families and they said, let's form an alliance. If one of you breaks apart, if one of you is gone, then our alliance would fall apart. So it symbolizes that. And it turns out that we can actually perform this grading of three types of anyons, right? And the fact that no two circles are linked pairwise, right? It means that if theoretically we find a phase that is non-trivial, right? It means that all three of these must have been non-Abelian, right? If one of these were Abelian, then it would only be sensitive to pairwise linking, so you wouldn't see a phase. So if you measure a phase of -1, that would be evidence that all these three were non-Abelian. So you can actually do that. We have some deep quantum circuit that actually does that, creates this pair. This is the space-time movie, right? And you could create this, braid around, and you find in the experiment a phase very close to pi. So that it gives us a very cool evidence that we prepared and confirmed a state which hosts these non-Abelian ions in the quantum device. Okay. So let me conclude. So I posed in the beginning of the talk, what can we do with measurements, right? And before that, what the community knew was that starting from an unentangled product state, we could prepare something like a toric code state, which is sort of Abelian gauge theory. But now using measurements, we can go further than that and reach these more interesting states called non-Abelian gauge theories. And the insight from that came from thinking of these measurements as a gauging procedure. And once we reformulated like that, we were able to access these interesting non-Abelian gauge theories. So I just have some slides of what I didn't talk about and what I'm thinking about next. Should I leave that for questions or should I?
Just take a minute.
Okay. Let's see. I did not talk about a couple things. Though this gauging actually hints at a actually more deep relation relating different things, including these non-invertible symmetries and symmetry protected topological phases. And in fact, you can understand this reasoning very clearly using tensor networks. So that's one thing I didn't talk about. We also studied the stability of the state preparation if you have errors. Yeah, let me just skip the details. And one thing you can also generalize this is to gauging fermionic theory. So if you have some actual physical fermions, you can do a generalization of this gauging called the Jordan-Wigner transformation, and you can even do that in higher dimensions, turned out. And one other thing we also discussed is interesting chiral phases that can be prepared using these protocols, but you might have to use not quantum circuits, but more general Hamiltonian evolutions. So for the future, I think what's very interesting is that people have really been thinking about topological quantum computation in solid state. But now that we are able to prepare these states directly in a quantum device, it begs the question, can we perform topological quantum computation in a quantum processor? Usually in a quantum device, people think of these usual error correcting codes, which are not topological. But now we can start thinking of using these non-Abelian anyons to potentially perform that. So that's an avenue to explore. On the more theory side, I already mentioned this, but what is the mathematics that classifies these phases under measurements? People have, for the unitary case, people understand that pretty well now, but on this case with measurements, it's still less explored. It would be interesting to prepare more interesting, say, non-Hermitian phases of matter, right? And you could also maybe think of generalizing measurements. I only talked about measurements today, but in general, non-unitary processes include these general quantum channels. Can we use that to our advantage to prepare more interesting states? And also a very broad open question, which people here are also thinking about, is how to define a phase of matter in open quantum systems. Okay. So really last slide, I just want to thank my collaborators, which is the theory was done towards the end of my PhD in Ashwin Vishwanath's group at Harvard. And Ryan and Ruben were postdocs there now. Ryan is faculty at UCLA and Ruben's a faculty at U Chicago. And this experiment was done in collaboration with Continuum. And I wanted to shout out to Mohsen Iqbal and Henrik Dreyer, who were our key forces in this experimental collaboration. Okay, so let me end there. Thank you.
All right, so earlier in the talk, you responded to a question by saying the number of non-Abelian simple groups in your groups, that's the difficulty of preparing one of these states. Is there, they're all, if you can't do it with this measurement method, they're all linear time.
Right. They're all different phases, that's why they're linear.
Okay, but you said somehow it was more preparing A5 versus A5 semi-direct A5. That one, the second one is harder.
Oh, no.
No,
They're equally hard, but also
Okay.
still different phases in this new language. So they will both be linear there, but to go to one another would also be linear.
I see. Okay, so every time you semi-direct product by not a Abelian simple group, that's a linear depth operation.
Yeah, or even just direct product.
Oh, okay.
There's two copies.
Because then it's just you have to prepare them.
Thanks for the awesome talk. I was wondering, like, you were trying to prepare a given gauge theory and you start with some symmetries of your system. Is there any kind of intuition you use to figure out what set of measurements and unitaries and like circumvent?
So I guess for us, what we did was there was a certain fixed point state which people have studied well, and we're aiming to reach that fixed point state. Now, in particular, if you already reached that fixed point, then you can apply local unitaries to reach anywhere else in the phase in principle. So we have not really optimized, like if you really want to lower the overhead of the constant, the coefficient in front of it.
Yeah, I kind of was thinking back on like the idea of like topological places, symmetries, and like open systems. So I guess like maybe like the simplest question is like, let's say you have a Hamiltonian and a Lagrangian that like they kind of prepare the same entangle state. Because like I mean, if you engineer Lagrangian in a smart way, you can also prepare like very high quality fields like with them. But if like they can prepare the same state, would that mean that the Hamiltonian and Lagrangian fall under the same symmetry class, or would they be different?
So what do you mean by preparing a state with the Hamiltonian? Just starting with the product state and evolving with that?
Yeah.
I guess it depends on how long you do, right? Of course, when people talk about Lagrangians, you're talking about the fixed point.
Yeah.
You can ask about in a finite time whether you are able to prepare that state or not. Because fixed point Lagrangian so infinite time. So I'm not sure how to do it.
Well, yes, if you can do it by like
I guess maybe sort of rephrasing that, a Lagrangian would be a way of expressing some like continuous time version of this, like even here you're measuring and finding unitaries.
Yeah.
You seem to show that you have to do a linear time evolution in a Hamiltonian picture, and then when you switch to the Lagrangian picture, you have to do the shorter time evolution to prepare the state. So like, why are the Hamiltonian and Lagrangian sort of not in the same? I don't know. So really say symmetry class.
Right, I'm sort of doing the discrete version of that instead of Hamiltonian evolution of the quantum circuit. So the analog of Lagrangian would be quantum circuit and tracing out the environment. Yes, that was equivalent to that. But maybe I'm not. Yeah, maybe I need to think about your question. I haven't really thought about the continuous version yet. I think it's worth thinking about.
Walls will be stronger cavity.
That's true. That's true. That's all.
Yeah, can you talk about like measurement fidelity and how that plays into this? So if you make some measurement wrong of your card, does that basically completely kill the ground state you're trying to produce, or does it do something with some fidelity still?
Right. So if your measurement was wrong and you recorded it incorrectly for each experiment you did, you would still get a topologically ordered state. It just has a charge there. But now if you're trying to measure expectation values and you average over your experiments, then that would mess up fidelity. But I guess it's two different questions.
Yeah, okay, I guess
It does not undermine the fact that
it doesn't
each
mind that
measurement
you have it, just don't have the one you thought you had.
Yeah, I was wondering whether any results on which states you can prepare efficiently depend on whether you assume the measurements to be local or not.
Currently here, we only assume local measurements, but what we're allowing is this feedback and the feedback could involve non-local stuff. So for example, this guy here has to communicate with this guy over
Sure,
there.
yeah. But like, is it possible that these like soccer ball like states, let's say, that are still seem hard to compare, that they could benefit from being able to measure some local?
I guess because measurement can already do teleportation, so you could do maybe.
I mean, like measuring some non-local parity, let's say, for example, like that change wasn't.
Yeah, I'm not sure. I have not thought of that. We could discuss that.
Thanks, yeah.
Just on a comment on that question, like if you're allowed like big general non-local measurements, couldn't you like measure in the eigenbasis of like the Hamiltonian, if you're like D4 Hamiltonian or something, but like.
Still might be exponentially unlikely.
But every state, like every option would be topologically ordered.
But actually, let me comment that for the toric code, let's say you're only unitary, and if you're allowed to do non-local gates that are like k-local but still finite range, you still cannot compare the toric code in finite. And the reason is sort of you have to build this sort of logical operator. You have to grow it from one qubit to the whole thing that goes around the system. So even if you have non-local, but you're still acting on finite things at a time. So
We need log.
I think the best is log.
Are you talking non-local or also multi-point?
Either, I guess, I was already wondering if just being able to measure them, yeah. But I guess they're all interesting. So, yeah.
Okay, yeah, so, let's end this, but there's lots of room on that schedule, so to sign up for a slot.
Okay.
But